Approximate forms of the current over potential equation. So here we have equation number 1 as current potential equation, in which I is the current generated at the electrode, which is controlled by the exchange current, whereas it is also showing the contribution of the cathodic and anodic component towards the overall current generated at the electrode. So here we can see that the current, that is the exchange current, which is defined as equation number 2, is directly related to the standard rate constant. So this equation is giving the generalized form, showing the contribution of cathodic and anodic component with respective concentrations of the oxidized and reduced species at the surface and the bulk of the electrochemical cell. So now let's discuss the first approximate form, that is no mass transfer effect. So what is the mass transfer? Mass transfer is the movement of the electroactive species that can be analyte or can be any other species from the bulk of the solution towards the electrode surface through convection, diffusion, and migration. Diffusion is observed due to the concentration gradient, and these different species are diffused in bulk, leading the flow of current in external circuit. Whereas for the case of migration, depending on the electrical potential, some charges move towards the electrode. It can be reduced by using higher concentration of the supporting or background electrolyte. Due to this higher concentration of the supporting or background electrolyte, the species tend to stay within the bulk. Otherwise, any effective charge that is generated at the surface of the electrode due to either oxidation or reduction of the species present at the surface may cause the movement of the species from the bulk towards the electrode surface, but due to the availability of this concentrated supporting electrolyte, the charge of the system is balanced, and the supporting electrolyte doesn't involve into the any charge transfer processes, which is known as the heterogeneous charge transfer from the solution to the electrode. Another important contribution of the mass transfer is due to the convection, that is the movement of the charges due to the mass transfer process is based on the density gradient. So overall, any kind of the mass transfer which can generate the non-Faradic contribution towards the overall current must be suppressed. So in that case, two main preventive measures can be used, that is increase the concentration of supporting electrolyte. The second is we can increase the ionic mobility of analytical species. The rate of mass transfer is for the anodic component is written as, that is mass transfer coefficient, and the concentration of the species within the bulk minus concentration at the surface of electrode. Similarly, the rate of mass transfer for the net cathodic reaction is given as that is the surface of electrode. For this one, x is 0. That is question number 4. So here we have two mass transfer processes which are occurring at the electrode surface, making the net contribution towards the anodic and cathodic reactions, in which m0 and m are the mass transfer coefficients for anodic and cathodic reactions. The unit of this coefficient is in centimeter per second. Now let's for the mass transfer control process in which the rate of mass transfers are negligible. So for this case, the concentration of the oxidized species within the bulk must be equal to the concentration of the oxidized species at the surface of electrode. Similarly, for that case, the concentration of the reduced species within the bulk must be equal to the reduced form of the analyte at the surface of electrode. These are for the case of nearly zero rate of mass transfer processes. So this condition is possible when the concentration of the analyte is low. So for this case, the ratio of the oxidized species less equal to 0.99 and the ratio of the reduced form of analyte at the surface of electrode over the bulk is almost equal to. So we can say that these ratios are equal to 1. So now we can reconsider this equation number 1, in which these ratios are equal to 1, and this equation number 1 is modified to so this equation 5 is known as Butler-Volmer equation. Now let's discuss this Butler-Volmer equation for different exchange current densities. Now here we have a diagram which is showing the effect of the current density on the activation over potential required to deliver net current densities. So these lines in the red color are showing the net current densities for various exchange current densities. So this equation known as the Butler-Volmer equation is a good approximation of this current over potential equation given as equation number 1. For the condition when the current is less than the 10% of the total limiting cathodic or limiting anodic current. So let's see the picture for the approximation of the current over potential equation, that is the Butler-Volmer equation. So here we have the limiting cathodic current and limiting anodic current, which is showing all the oxidized and reduced form of the analyte species have been reduced or oxidized. So for the first approximation, which is showing the mass transfer control process is within the range at which the current, that is the total current, is less than the 10% lower than the limiting cathodic current. So these currents are actually the currents in shown in the red color are actually the less than 10% contribution of the total cathodic or the anodic components of this current over potential equation. And here we have 3 different exchange current densities. For each cases, the number of transferred electron is 1 and alpha is 0.5. It means that the symmetry of the potential barrier is symmetrical. Here one more thing is needed to remember, that the over potential or eta is actually equal to the difference of applied potential and equilibrium potential. So in each case, since the mass transfer effects are not included here, the over potential is associated with any given current given at y-axis. So here any applied potential will serve as the activation energy to generate these currents. Simply we can say that the applied potential is contributing to the sole generation of current, and it's not utilized for any other processes like mass transfer processes. So this over potential is required to derive the heterogeneous charge transfer at the rate which is reflected by the amount of current generated, shown with red lines, as the rate of heterogeneous charge transfer is directly related to the current generated at the electrode. So we can say that the amount of potential applied to the electrode is only involved in the heterogeneous charge transfer, which directly show the rate of heterogeneous charge transferred in a form of current generation that is shown in the figure as red lines, which is then related to the exchange current. Lower the exchange current, lower will be the current generated, and sluggish will be the rate of heterogeneous charge transfer. So here for a particular applied potential, when the mass transfer effects are suppressed, the applied potential is involved in the generation of current that is then related to the rate of charge transfer, that is the heterogeneous charge transfer, and which is also related to the heterogeneous or the standard rate constant, and this rate constant is directly related to the exchange current through the expression as equation number 2. So according to that, lower the exchange current, sluggish will be the kinetics. Hence we need to apply the larger activation over potential for any particular net current. So for very large exchange current, the rate constant value is higher, generating the higher current that depict the higher rate of the heterogeneous charge transfer will require a lower value of over potential activation energy. So now let's take the example of the case A, which is shown as a red line, is showing the vertical current sweep. For this case, the system can apply the large current supply, perhaps even the mass transfer limited current. So this system require insignificant activation over potential that can be viewed as activation energy. So for this case, we haven't a need to supply the activation over potential, that is a form of activation energy, to generate the current for the particular charge transfer, that is the heterogeneous charge transfer. So initially the current will be generated, and if the system is mass transfer controlled, then the current generation will be lowered, as all the species will be either oxidized or reduced. So for this case, the continuation of current will require the movement of or bulk movement of the species towards the electrode in order to maintain the current generation. So the current generation will be continued as the species will tend to move towards the surface of the electrode without application of any activation energy in a form of over potential. For this case, the limiting current will reach within the few tens of millivolts, 10 millivolts of the applied over potential. Now let's consider the other extreme, and that is shown as the plot C. That is the exceedingly small exchange current that is due to the very low value of the standard rate constant, and it will require a very large activation over potential. So as shown here, like it's above -300 for the cathodic component of the current, and above 300 millivolt for the anodic component of the current. So in this circumstance, that no significant current is observed unless a very large activation over potential is applied. And for this kind of charge transfer, a sufficiently extreme over potentials will be applied until we get the limiting current. So at a sufficiently extreme potential, the heterogeneous process can be driven fast enough that the mass transfer controls the current, and this limiting plateau is reached. Now come back to the current over potential plot, which is showing the limiting current plateau, which is controlled by the mass transfer processes. If the mass transfer process is observed, this plateau cannot be observed, as the species from the bulk of the solution will continue to reach at the surface of electrode, causing the interfacial charge transfer and generating the current. So this current plateau will not be obtained, and making the current rise continuously until all the analyte species have been reduced or oxidized. So for this case, that is the plot C, for the reduction of the species, a large negative potential is required, and for the oxidation of the species, a large positive over potential will be required. Whereas B is showing the intermediate case. In three cases, we have seen that the exchange current is a measure of any system's ability to deliver a net current without significant energy loss due to activation. In real system, exchange current densities reflects the wide range of the standard rate constant, and they may exceed from 10 ampere centimeter square to picoampere per centimeter square. So here we have these three plots which are showing the symmetrical energy barrier, where the alpha was 0.5, which is known as the transfer coefficient. Now let's consider different values of alpha. When alpha is 0.5, that is the transfer coefficient, which shows the symmetric variation of the current with application of the either negative or the positive over potentials. For symmetric transfer coefficient, the amount of over potential required for the specific amount of cathodic current will be equal to the amount of positive over potential required for the anodic current with same value. Whereas for alpha that is less than 0.5, the large negative over potentials will be required for the generation of cathodic current as compared to the smaller required over potentials for the generation of similar amount of current. for anodic component, and for alpha, which is greater than 0.75, the large positive overpotentials will be required for the generation of anodic current. For example, for the 4 microampere per centimeter square, it will require almost around 175 millivolt, and for the same current it will require almost 100 millivolt, that is the negative current or the cathodic current with the application of negative voltage. So in this lecture we have discussed the effect of the transfer coefficient on the symmetry of the Butler-Volmer equation plot, and here we also observe the effect of the exchange current that is directly related to the rate of the heterogeneous charge transfer and inversely related to the overpotential activation energy.